Have you ever wondered how the heliocentric model elegantly explains the tangled, looping trajectories of wandering planets? All these complex cosmic effects arise due to the differences in planetary velocities around the Sun. It turns out that Earth simply periodically overtakes superior celestial bodies along its inner, faster orbit. It is precisely during these moments of mutual overtaking that the planet appears to reverse its direction to the observer.
For as long as we've looked up at the night sky, we've seen this incredible, predictable order. The stars, they move in a perfect procession. But there were always a few points of light that just refused to play by the rules. The ancient Greeks called them planetes, the wanderers. And their strange, looping paths were one of the greatest mysteries in science. Today, we're going to break down the elegant physics behind what looks like, well, celestial chaos.
So here's our roadmap. First, we're going to really define the puzzle of these wandering stars. Then we'll build up a common language to describe what we're actually seeing. That's the geometry of configurations. From there, we'll apply these ideas to the inner and the outer planets. And finally, we'll put it all together to solve that great illusion of retrograde motion.
All right, so here's the fundamental problem that kept astronomers up at night for centuries. You have the fixed stars, wheeling overhead in perfect unison. But then you have the planets. They'd drift eastward against that starry backdrop night after night, but then they'd slow down, stop, and actually start moving backward for a while before going forward again. What on earth could possibly explain that?
Well, the answer really begins the moment we realize we aren't stationary observers. Not at all. We are all passengers on a moving spaceship called Earth, and we're watching other moving spaceships, the planets, as we all race around the Sun. It's this incredibly dynamic cosmic dance, and the angles and the distances between all the dancers are changing literally every single second.
Now, to make any sense of this dance, we first need some specific language. We need names for the key geometrical alignments that happen between the Sun, the Earth, and another planet. In astronomy, we call these special arrangements configurations.
So let's be clear about what a configuration is. It's not just where a planet happens to be in its orbit. It's a moment of a very specific, special alignment. Kind of like what you're seeing in this diagram here. It's these moments that create unique viewing opportunities from our vantage point on Earth. And you know what? Understanding them is the key to unlocking everything else.
Okay, our first key configuration is called conjunction. As this diagram shows, it's pretty simple. It's when a planet lines up in the same direction as the Sun from our perspective. What that means for us on Earth is that the planet is pretty much lost in the Sun's glare, making it impossible to see. Now, as we're about to find out, this can actually happen in a couple of different ways. Next up, we have opposition. Now this is when things get interesting. Opposition is when the Earth is positioned directly between the Sun and an outer planet, like Mars or Jupiter. This is a fantastic time for astronomers because it means the planet rises right as the Sun sets. It's up all night long, shining at its brightest. Now for a term that only applies to the inner planets. We're talking Mercury and Venus. Because they orbit inside of Earth's path, they never seem to wander very far from the Sun in our sky. Elongation is the moment they reach their greatest angular distance from the Sun. This is when we see them at their peak, as a brilliant evening star just after sunset or a morning star just before sunrise.
And our final term is quadrature. Again, this one only applies to the outer planets. Just look at the diagram. It happens when the Sun, the Earth, and the outer planet form a perfect right-angled triangle, with that 90-degree angle right at Earth. From our perspective, this means the planet is high up in the southern sky at either sunset or sunrise.
Okay, so let's put it all together on one slide. This is our complete vocabulary. On the left, you've got the inner planets, which have two kinds of conjunction and those maximum elongations we talked about. And on the right, you have the outer planets, with their own unique set of configurations, conjunction, opposition, and quadrature. It's this fundamental difference in their geometry that explains why they look so different to us.
So let's take this new framework and apply it. We'll start with the inner, or as we sometimes call them, the inferior planets, those that are nestled between Earth's orbit and the Sun.
The journey for an inner planet follows this really predictable cycle. It starts out as superior conjunction, totally hidden behind the Sun. Then, as it continues in its orbit, it emerges into our evening sky, getting further and further from the Sun until it hits its peak visibility at eastern elongation. After that, it swings between us and the Sun at inferior conjunction, disappears, and then reappears in the morning sky on its way to western elongation.
And check this out.
This slide shows a really fascinating consequence of that orbit. Look at the huge difference in its distance from Earth. At inferior conjunction, when it's passing between us and the Sun, it's at its absolute closest point to us. Through a telescope, it would look its largest. But then, at superior conjunction, it's on the complete opposite side of the solar system, and it appears its smallest.
All right, we've looked inward. Now let's turn our attention outwards, to the superior planets, those whose orbits lie beyond our own. So, the rhythm for an outer planet is a little different. It also starts at conjunction, hidden from view behind the Sun. It then moves through eastern quadrature, but the main event, as we've talked about, is opposition. That's when we are perfectly lined up between it and the Sun. After opposition, it continues its journey onto western quadrature before beginning that long trip back to conjunction again.
And this slide just illustrates brilliantly why opposition is the prime time to observe these planets. This is the moment when an outer planet is at its closest approach to Earth. That means it's going to appear bigger and brighter in our sky than at any other time in its orbit. It's truly the moment every astronomer is waiting for.
So we now have all the tools we need. We've got the geometry, we understand the configurations. Now we can finally tackle that central mystery, the illusion of retrograde motion. It's time to bring some physics into the picture.
Let's just state the question one more time, as plainly as we can. For most of the time, we see planets moving forward, from west to east, against the stars. We call that prograde motion. But for a little while, they seem to slow down, stop, and actually move backward, from east to west, before carrying on again. Why does this happen?
The answer isn't some strange, mystical force. It's actually a pretty basic concept from physics: relative velocity. It's the exact same reason that when you're driving on the highway and you pass a slower car, for a brief moment, that other car can actually look like it's going backward. It's all just a matter of who is moving faster.
And here it is. This simple chart is the key that unlocks the entire mystery. The laws of gravity just dictate that the closer a planet is to the Sun, the faster it has to move to stay in orbit. So Venus moves faster than Earth and Earth moves faster than Mars. This simple hierarchy of speed, that's what explains everything.
So here's exactly how it works. For an outer planet like Mars, when it's near opposition, both Earth and Mars are moving in the same general direction. But because Earth is on the inside track and moving faster, we literally overtake it. And from our moving perspective, the slower outer planet appears to drift backward against the very distant stars. And for an inner planet like Venus, near its inferior conjunction, it's the other way around. The faster-moving Venus overtakes a slower Earth, but it produces the exact same visual effect.
And this completes the entire picture. So what about the rest of the time, when a planet is on the far side of the Sun, near conjunction? Well, then we and that planet are moving in opposite directions relative to each other. From our point of view, our speeds essentially add up, which is why the planet appears to move steadily forward across the sky. That's the normal or prograde motion we see most of the time. So, to be perfectly clear, the planets are not actually stopping and reversing course. Their orbits are smooth. They are continuous ellipses. The complex, looping dance we see in our sky is a beautiful, and more importantly, a predictable illusion. It's a parallax effect created by our own moving vantage point inside a solar system that is governed by the unchanging laws of orbital mechanics.
And that really brings us to our final thought. This elegant physical explanation, based on nothing more than relative motion, is so profoundly different from the complex, Earth-centered models of the ancient world, which had to invent circles spinning on other circles to explain what they saw. So the question I want to leave you with is this: how did this simple shift in perspective, this solution to the wandering stars, not only solve an age-old puzzle, but also completely revolutionized our understanding of our place in the entire universe?
Thank you, friends. Strive for understanding and become wiser. See you soon.